Wednesday morning. We survived the first third of the semester. Judging by the number of empty desks, we had quite a few casualties. Unless they're just like. Now we begin our second third. We start by looking at rational functions. So the definition of a rational function is a function of the form p of x over q of x, where both p and q are polynomials, and q is not the zero polynomial. So rational functions are exclusively a polynomial over a polynomial. Domain is all real numbers except those that cause the denominator to be 0. In mathematical notation, it is the set of all real numbers x such that q of x is not 0. And that was something that we already knew. So, notation. So this notation is going to be important. This means that x approaches a from the left. X approaches a from the right. And notice what they don't say. They don't say that x is a. So for that conversation, x will never be a. We've already kind of seen this. This means x is increasing without bound. X is decreasing without bound. And we also saw those. F of x increase without bound, F of x decrease without bound. Finally, f of x is approaching the value of a. Again, it is important to note that for that last notation, f of x doesn't necessarily have to ever equal a. All it's doing is it's approaching the value of a. You should be familiar with a vertical asymptote. So if I give you the graph of a function, would you be able to identify vertical asymptotes from it? That's troubling. It's also troubling. What are they teaching in algebra these days? Plot of 1 over x. Can you identify the vertical asymptote? What is it? Right, so you know what a vertical asymptote is. Right? You can identify. You knew they taught this. You may have a trouble of actually defining it. That's okay, because that's what we're going to do right now. Vertical asymptote is a vertical line x equals a, where the graph tends toward either positive or negative infinity on either side of x equals a. Using the notation, this is what that's saying. You would say that x equals a if that statement is true. And remember, in math, or is an inclusive or. So that means one or the other or both to make the statement true.
Do you have a shotgun in your vehicle?
Police Academy.
Sure.
So, true or false? A function can touch its vertical asymptote. So I give you that second graph. Does that graph make that above statement true? Does the function tend to either positive or negative infinity on one of the sides? Which side? The right. You come in from the right. So since that statement is true, x equals 0 is a vertical asymptote. But we're touching the vertical asymptote. That is allowed. That would still be a vertical asymptote, x equals 0. What's not allowed is crossing the vertical asymptote. Then it wouldn't be a vertical asymptote. Or you touch it on both sides. Then it wouldn't be a vertical asymptote. So it is possible for the graph to touch it, just not cross it. Using the language of calculus, which is the better way of defining a vertical asymptote. We use the notion of limits, which is exactly what the previous statement is saying, just more concise. Again, that's the very first thing that you'll study in Calc 1 is the notion of a limit. Hopefully you have someone who teaches you the formal definition of the limit, so you can really understand what a limit is. Unfortunately, I don't have high hopes for that, because not a lot of people teach it. Horizontal asymptote. So again, this would probably be something that you would be able to identify if I gave you a graph. Actually, plot. Each one use the same one. Can you identify the horizontal asymptote?
Y is equal to 0.
Y equals 0 would be a horizontal asymptote. Horizontal asymptote of a graph is a horizontal line y equals b, where the graph approaches the line as the inputs increase or decrease without bound. Again, using notation, as x approaches plus or minus infinity, f of x would approach b. Can a function touch its horizontal asymptote? So what do you think? Would it be able to touch the horizontal asymptote? Yeah. Can it cross it? I'd say no.
It would still be a function, but I have no idea how you would make that a function.
horizontal asymptote is 0, but it does cross it. Is there a limit on how many times it can cross the horizontal? It could theoretically cross it an infinite number of times. Right, because all we're concerned with the horizontal asymptote is what it does as x increases or decreases without bound. It says nothing about what it does in the middle. Zero would still be an asymptote. It would still be a horizontal asymptote, even though it crosses it several times. And that would be the notation of calculus. And again, only one of those has to be true. So if we look at that top plot and we just cut out the left, 0 is still a horizontal asymptote. Because as x increases without bound, it's approaching infinity. It can also have two different horizontal asymptotes. Right, whatever those two lines happen to be, they're both horizontal asymptotes. Oh, okay, yeah, you can see it, just barely. Instead, that might be easier to see. To determine if a function crosses the horizontal asymptote, what would you have to do? Not just necessarily cross, touches it.
If you get an x value when y is equal to
Yeah, set fx equal to b and solve for x. If you get a solution, then it's clearly going to touch it. Right, idea of continuous. Right, so clearly that first plot up there is not continuous. However, the other ones that I drew were continuous. So removal of discontinuity would occur in the graph of a rational function at x equals a if a is a 0 for a factor in the denominator that is common with a factor in the numerator. In other words, if you get rid of the 0 in the denominator, it would no longer be an asymptote. It would be a hole, which is a removable discontinuity. Right. However, if the multiplicity is greater in the denominator than it is in the numerator, then you're not going to be able to get rid of that 0 in the denominator, and so you'd still have the asymptote there. It wouldn't be a hole. So when sketching a rational function, the graph of a rational function, you want to first determine domain, determine any vertical asymptotes, along with any holes, and then determine end behavior. Oh, and your intercepts, see if it crosses the x or y axis. I'm not going to focus on sketching. So determine vertical asymptotes. For rational functions, you will have a vertical asymptote whenever the denominator is 0. Right? And you can't get rid of it. So set the denominator equal to 0 and solve. X squared minus 4 is 0. X squared is 4. Which means the absolute value of x would be 2. There are 2 vertical asymptotes. X equals -2 and x equals +2. Remember that asymptotes are lines. So when you write them out, that has to be in the form of a line. You can't just write vertical asymptote -2, +2. Those are points, not lines. You have to write out x equals -2. X equals +2. x squared plus 4 is the denominator. Set it equal to 0. What's wrong with that statement?
The complex number. You gotta take the square root of -4.
Even before that. That's saying that the sum of two positive numbers is 0, which is a contradiction. Right? But yes, if you actually solve for it, that's what's going to wind up happening. So right away you can tell that statement is not true. You can't sum two positive numbers to get 0. That means there's no vertical asymptotes. Another way to do it, probably a better way. Fully factor the numerator and the denominator. Can you factor the numerator? Can you factor the denominator? Factor it. What does it factor to?
X minus 2 and x plus 1.
Is there a common factor? Now use that factored form. Where does the denominator equal 0?
And x equals 2, x equals -1.
Those are your vertical asymptotes. No, we know there's not going to be any common factors. Factor the denominator. This is a special product from algebra.
X plus 2 times x squared minus 2x plus 4.
Minus 2x, you said then what?
Plus 4.
That is its factored form. Sum of cubes. What are the zeros of the denominator? Say positive 2 is 0. Is that it? It is. X cubed plus 8 will only have one real 0, negative 2. The other two zeros are complex. Which of course does mean you have to be careful. It's kind of late now because this had the first test. For the quiz that's coming up. Because zeros will be on that quiz. X cubed plus 8, if I ask you to find all of the zeros, and you just try to go, well, x cubed is negative 8, so x has to be negative 2, you're missing 2 zeros. Can we factor the numerator?
Yeah.
How's the numerator factor? How does the denominator factor? Special product from algebra. One that you should be familiar with.
X plus 1 times x minus 1.
That one's the difference of squares. Is there a common factor? Would that be a true statement? We touched on this.
I would say yes. Say yes, that might be true.
Okay. Let x equal 1. What's the left-hand side? x equals 1. Left-hand side. What's the numerator?
0.
What's the denominator?
0. It's undefined.
Get 0 to 0, that's undefined. What is the right-hand side?
1/2.
Are they the same?
Nope.
That's a false statement. Now it's a true statement. As long as x is not 1, those two are identical. But at x equals 1, they won't be. Now, find the zeros of the denominator.
X equals 1, x equals -1.
But we can get rid of the x equals 1. Right? Because you have an x minus 1 in the numerator as well. So 1 is not a vertical asymptote. You only have one vertical asymptote at -1. X equals 1 is a whole. So when you go to sketch the graph at x equals 1, so the ordered pair would be 1, 1/2, you draw a hole. You draw an open circle. Horizontal asymptotes. For rationals, it is easy. Because it's going to do the same thing on both ends, for the most part. But I'm still going to consider each piece individually. So I'm going to introduce new notation. The double greater than sign means it's much greater than. So for x much greater than 0, well, the numerator is not going to change. But the denominator, if you take an extremely large value of x and square it, it's going to be extremely large, right? Add 4 to that. Is it really going to notice? And so think of an extremely large number, add 4. That 4 is kind of negligible. So for extremely large values of x, we can say the function behaves as 4x squared over x squared, which is what? Which is just 4. Y equals 4 would be a horizontal asymptote. Right, because then what this statement means is that. So if you let x get very large, then f of x is going to tend towards 4x squared over x squared, which is just 4. Pretty sure you can figure out what that notation means. Or much smaller than, or something along those lines. Well, again, the numerator is not going to change. The denominator. Take an extremely large number in the negative direction. Square it. Well, now you're going to have the exact same effect as if x was much larger than 0. Grab a single horizontal asymptote at y equals 4. It's not difficult to show using calculus that if f of x is approaching some finite value as x approaches infinity for a rational, so where f of x is rational, then it's approaching the same value as x approaches negative infinity. So as long as the value is finite, it's going to do the same thing on both ends. That's not difficult to show. So honestly, I just need to check one of them. But I'll continue to check both of them. So if we let x get very large, so x tends towards infinity, f of x, how's it going to behave? Well, the numerator will still behave like x squared, right? The denominator, well, take an extremely large number, add 4, it's the same argument. It's going to wind up just behaving like x. Which is what? Oh, but wait, as x, gets really large, what does x do? Gets really large. So there's no horizontal asymptote on the right. On the right-hand side, the graph is just going to keep increasing without bound. That's what this is saying. All right, so x squared still tends to x squared, but x plus 4. So again, take an extremely large number in the negative direction and add 4 to it. All right, so again, I'll use this example. It should be an example near and dear to. Do I have anyone who's in a medical major? Law? Oh, bummer. Let's say we have a med student. They just graduated and they took out $500,000 of student loans. They make a $4 payment. Did that really do anything? You still essentially have $500,000 in debt. Well, I've heard stories of med students coming out with over $1 million in student loan debt. Now, granted, they went into a really good field like anesthesiology that makes $600,000, $700,000 a year. So that's not too terrible, I guess. I'd tackle that debt in 3 or 4 years. That's still, I hate to get that bill. And that's X. It'd be particularly stupid to go $500,000 in debt when you make a minimum wage job, making $30,000 a year. You're going to be bankrupt by year's end. Actually, pretty sure on $1 million, the student loan payment would be more than your monthly income at $30,000 a year. The interest alone would probably be more than your monthly income, to be honest. That tends to minus infinity. So there's no horizontal asymptote. I'm going to go back real quick. So I want you to look at that function from the previous. And I want you to notice something about the numerator and the denominator. And notice what we got as a horizontal asymptote. Okay. Now I want you to notice something about the numerator and denominator here, and notice what we got as a horizontal asymptote. And we'll see if we can connect it. I want you to do the same thing here. I want you to notice what we have about the numerator and the denominator, how they would compare, and then what we're going to get as a horizontal asymptote. And keep doing that for each problem, see if you can make a connection. That's what math is all about, by the way. Noticing patterns and making connections. So as x gets very large, 2x tends to 2x. X squared minus 4 get a very, very large number and subtract 4. Again, you go back to the $1 million in student loans, and you make a $4 payment. It doesn't even notice it. It's like a little burp. Or it'd be like, you have $1 million in your bank account, and you give $4 to someone. Do you even really feel that you just gave $4 to someone? So that would behave as 2 over x, right? Now, what does 2 over x do as x gets very large?
Approaches 0.
It tends to 0. Right? 2 over x, 2 over an increasingly large number, gets increasingly smaller. Same argument. You have a very large number in the negative direction. 2x still behaves as 2x. X squared minus 4 would now behave as x squared, which is 2 over x. How's that going to behave? Let's start listing out values. 2 over negative 10. 2 over negative 100. 2 over negative 1,000. 2 over negative 10,000.
So it tends to 0.
That's also tending to 0. We have a single horizontal asymptote at y equals 0. So x is increasing without bound. How would 3x squared plus 5x plus 2 behave?
It's going to approach infinity.
True, but that's not what I'm looking for.
That's not what you're talking about.
Think back to when we were doing polynomials, when we were determining end behavior. What did we look at, and why did we look at it? So if you want to determine the end behavior of the numerator, what term would you look at to determine it? Remember what we did? That was for finding zeros. I'm talking about just the end behavior. When we first started studying polynomials. Which again, you just took an exam on. I don't remember if end behavior was on it though.
power is 2. It's even.
Why are you looking?
Coefficients positive.
Why are you looking at that term though? So that's the leading term, right?
Yeah.
That's the term you focus on.
Right.
Why is that the term you focus on? Do you remember? All right, so think of it. Take an extremely large x value. Think of the largest number you can think of. Largest named number that I know is the Googleplex, which is a 10 raised to a Google. And so 10, so a 1 followed by a Google zeros. And a Google is a 1 followed by 100 zeros. So that'd be 10 to the 100 power. So a Googleplex is 10 to the 10 to the 100. It's a very large number. Square it and multiply by 3. Right, so 10 to the 10 to the 100 squared is 10 to the 20 to the 100. Multiply that by 3. You're looking at 30 to the 20 to the 100. 5 times 10 to the 10 to the 100 would just be 50 to the 10 to the 100. Does that really impact the first term? Not really. Take 30 to the 20 to the 100 and add 2 to it. Does it even freaking notice? No, it's like you run into an amoeba. Do you even notice that you just killed an amoeba? No. You probably won't even notice if you step on an ant, to be honest. That's why we focus on the leading term, because that leading term dominates for extremely large values of x. Which means 4x squared plus 1 would behave as what for extremely large values of x?
4x squared.
It would just be 4x squared, wouldn't it? What is that? Which tends to 3 over 4. So 3/4 would be a horizontal asymptote. And it would be the same argument as we let x decrease without bounds. We let x get extremely large in the negative direction. The 3x squared in the numerator is dominating. Right? The other two terms don't even matter. In the denominator, your 4x squared is your dominating term. So it still behaves as 3x squared over 4x squared. Which is 3/4. So y equals 3/4 is our horizontal asymptote. And again, it's not hard to show that for rational functions, if you have a horizontal asymptote, it's unique. It's the only one. A rational function will not have more than one horizontal asymptote. That is not difficult to show. So as you work on the homework and the practice exercises for horizontal asymptotes, just keep an eye out on how your numerator and denominator relate versus what you get as a horizontal asymptote. And see if you can make that connection. Vertical and horizontal asymptotes, are they the only asymptotes? No. there are theoretically an infinite number of types of asymptotes. However, all the other asymptotes behave like a horizontal in that it's what is the function doing on the end. So for rationals, which is what we're looking at right now, you have what's known collectively as curvilinear asymptotes. Horizontal asymptote is a curvilinear. It's a special type of curvilinear. All curvilinear means is it's a curve. So we could have a parabolic asymptote, right? It'll behave kind of like an x squared function, a quadratic function. Could have a cubic, could behave like a cubic function. Could have a fifth degree. Right, so on the end it could behave like a fifth degree polynomial. We generally ignore those because they're not really that interesting, at least not at this level. They become very interesting in a more advanced study of functions. So if you start looking at more advanced types of functions, now your curvilinear asymptotes look really interesting. No. I never studied curvilinear asymptotes in depth. And remember, I have a grad degree. So it kind of shows you the niche that they fall in. If you would study them at all in undergrad, it would be a very specialized class. You'd probably doing independent research or independent study. Right? It would just be a very specialized class. There is one curvilinear we do look at because it is interesting. That's called the slant asymptote or the oblique asymptote. And that is a first degree polynomial. It's a line. It's linear. So yes, technically your function is increasing and decreasing without bound, but it's doing so approaching a straight curve, a line. And they occur in very special circumstances. First and foremost, there cannot be a horizontal asymptote. Right? You can only have one type of curvilinear. Yeah, for rational functions, you can only have one type of curvilinear asymptote. So if you have a horizontal, you can't have a slant. If you have a slant, you can't have a horizontal. Now again, when you study more advanced functions, you can have multiple curvilinears. Specifically, they're going to have two, right? Because x can only either increase without bound or decrease without bound, right? You only have a right or a left. So the first thing you want to do is determine, does this have a horizontal? Here's another way of determining that. Would that rational function be what's known as proper? So a proper rational function is one. No, one. I don't think the book actually defined it, but I probably should add it to my future notes. It is proper if the degree of your numerator is less than the degree of the denominator. So again, very similar definition to what a proper fraction is. Proper fraction is your numerator smaller than your denominator. Same kind of idea. If a rational function is not proper, it is obviously improper. So come back to here. Is this proper? It's improper. Perform long division on it. Or in this case, you can just perform synthetic, right? This allows us to rewrite the function as x minus 4 plus 16 over x plus 4. As x increases or decreases without bound, that 16 over x plus 4 is going to do the same thing. So just look at one direction. If you let x get increasingly large, what's happening to 16 over x plus 4?
Sounds towards 0.
Which would mean that f of x tends to x minus 4. That's your slant asymptote. That's linear. So that's your slant asymptote. So this rational function would have a slant asymptote, y equals x minus 4. Because again, as we let f of x increase without bound, or not f of x, I'm sorry. As we let x increase without bound, your function is going to start to mimic that line. Right? Because that remainder part, that 16 over x plus 4, is going to start to become negligible. By the way, the remainder will always tend to 0 as you let x get larger. Because the remainder itself will be proper. So, what is the difference between the problem we just did now and this one? There's only one difference. What is the difference in degree here between the numerator and the denominator?
1.
Right, numerator is larger by 1. Here it's larger by 2. Let's see what happens. Again, because the denominator is linear, we can use synthetic. Oh, I did it right, plus 16. 16 times -4, -64. This would allow us to write f of x this way. That again would tend towards 0, right? Which would mean that f of x itself is going to tend towards x squared minus 4x plus 16. Is that linear? No. Linear would have to be degree 1. That's degree 2. No sign asymptote. In this case, we do have an asymptote, it's the parabolic asymptote. But we're ignoring that for this class. There's no sign asymptote. Now, why did I say you can always use this method? Because if you go back, if you perform long division on this, notice that first off it's proper. Your quotient is 0, isn't it? And your remainder would be that. Well, that remainder is going to tend to 0, which makes your quotient the asymptote. Y equals 0. Take this one. Perform long division on that. Your quotient is going to be 3/4. I don't know what the remainder is going to be, but I know the remainder is proper, which will tend to 0. Which means 3/4 would then be your horizontal asymptote. So for rational functions, whenever you perform division, your quotient is your asymptote, your curvilinear asymptote. And so again, that's why I said this method will always work. And so what about here? Well, here we're not going to be able to perform synthetic division, right? So we're going to have to use long division. What is the first term of the quotient? No, that's the dividend. Quotient. So what do you have to multiply 2x by to get x squared? Half x. That's your first term of the quotient. Perform out that subtraction. -5 plus 5 halves. negative 5 halves x. And then 3 minus 0 is 3. Does that term have a smaller degree than the divisor? No, same degree. So we have to do it again. What is the next term of the quotient? So what are you multiplying 2 by to get negative 5 halves? I need a calculator. That's sad.
It's 5/4. Negative 5/4.
At this point, I don't really care about the remainder, but I'm still going to find it. Three minus 25 over 4. Negative 13 over 4. F of x can be written this way. Fx minus 5/4 minus 13/4 over 2x minus 5. Which of course is a complex fraction. So really that should be this. 13 over 4 times the quantity of 2x minus 5. So as x continues to increase or decrease, that remainder tends to 0, doesn't it? Which would mean that f of x tends towards the quotient. Right? So for very large values of x, f of x behaves like the quotient. That is your asymptote. Is that linear? Yes. So that's your slant asymptote. Now here we definitely can't use synthetic because the divisor is not linear. So you can't even cheat. I don't feel like doing this way. So I'm going to. testing on if you can divide polynomials anymore. So I'm going to cheat. Oh, wait. Oh, we're going to find out. I think about it, I don't know if your calculus knows how to do this. And you, algebra. Oh, no, it can't. Oh, that sucks. I actually have to do this by hand. That's so annoying. Oh, wait. No, no. I don't think that's going to work, though. Let me find out. Fraction. Will it do it? Please do it. Please do it. Let me do this one. No! That's annoying. Oh, that's. Well, my calculator can do it. What are we multiplying x squared by?
2x.
We get 0 minus 4x squared, negative x minus 2x, same degree, go again. What do we have to multiply x squared by?
-4.
5x plus 4 is what we're left with. And that means f of x becomes 2x minus 4 plus 5x plus 4 over x squared plus 2x plus 1. And so if we look at the remainder as x gets either very large or very large in the negative, that would tend towards 5x over x squared, right? Which is 5 over x, which tends to 0. And so that's what I mean. The remainder is always going to tend to 0. So f of x itself tends to 2x minus 4. Is that linear? Then that's a sine asymptote. By the way, you can still determine whether your function crosses the sine asymptote by still setting your function equal to it and solving for x. It's just a bit more difficult now. algebraically speaking. Any questions? So you do have a homework due tonight. That is the zeros of polynomials. Third discussion is off. Initial posts are due the 10th, tomorrow. Replies are due the 14th, and replies are not to be posted before the initial post is due. So replies start on the 11th.